I am pleased to present the work performed at the Institute of Continuous Media Mechanics, the city of Perm, Russia. Our work concerns an experimental study of the mechanical state of concrete structure in which inelastic deformations involve. Experimental studies of the critical deformations of reinforced concrete structures are necessary to ensure their safe operation. The peculiarity of these structures is that they consist of the elements of different sizes, which interact with each other. For this reason, testing of individual fragments of structures cannot reproduce the whole variety of deformation processes in them. This is especially true when critical processes arise and involve in some parts of the structure. Therefore, it is necessary to study such phenomena using samples that are close in size and design features to real prototype. Here we present the results of our experiments with a model concrete structure subjected static load. The main goal of this study is to trace the change in the mechanical state of the structure over its entire life cycle, from the elastic state to the total destruction. We would like to find the precursors of failure and to detect their location. The model object is shown in the figure. It is a 4-story reinforced concrete building. It has the following dimensions: length is 6 meters, width is 8 meters and height is 6 meters. Here we see the scheme of the experiment. The picture represents a half of the building with sensors placed on it. Static load is applied by means of a jack, installed between 2 floor slabs. The loading process is carried out stepwise, with increasing the load at each step and reset to 0 before the next step. The deformation response of the structure is recorded using sensors of 3 types. The vibration diagnostic procedure is performed after each loading step when the structure is unloaded. Excitation of vibrations is performed using a striker of 470 grams. The place and direction of the impact is shown by the orange arrow. Acoustic emission signals are recorded continuously, excluding impact period. This slide demonstrates the deformation response of the structure to a localized static load during 8 initial loading steps. We can see that the strain value decreases rapidly when the distance from the loading point increases. We propose to characterize the deformation response to the applied static load using the coefficient K. For a specific point of the structure, it is equal to the ratio of applied force at a certain loading step to corresponding local strain. This coefficient changes at each loading step, and we can trace how this value varies with increasing load. These diagrams show changes in the deformation response coefficient when the static load increases from 0 to 160 kilonewtons. The curves obtained at various sensors look different, but we are interested in the graphs related to the points near the jack, sensors number 1, 2 and 3. Here you can see a sharp break in the curves when the load is about 80 kilonewtons, for the sensors 1 and 3 located at the same level, are the load about 120 kilonewtons, for the sensors 1 and 2 installed at different levels near the jack. We suppose that these features of the curves are associated with the appearance of local damages in the area of the static load application. Another method used to record structural damages is the vibration diagnostic. After each loading step, structural vibrations were excited, and the acceleration vibrograms were obtained and compared with the vibrograms recorded prior to loading. Here we can see the vibrograms obtained for the sensor number 7 located on the column near the jack. The vibrograms of the first 2 loading steps are almost identical. But vibrograms of the first and the last step are significantly different. This slide analyzes the results of the Fourier transform of acceleration vibrograms. The figure on top compares 37 Fourier spectra of vibrograms obtained after consecutive loading steps. The largest discrepancy between these curves is observed at the frequency of 0.36 kHz and 1.62 kHz. We can trace how the amplitude of the spectrum changes after each loading step when the frequency is equal to one of these values. The graphs in the bottom show how the amplitude changes with increasing load. Here we see the amplitude evolution at 6 different points of the structure. These points are located on various structural elements. All curves have noticeable bends near the forces of 80 kN and 120, 130 kN. This behavior is recorded both by sensors close to the jack and on remote ones. We associate these peculiarities with the damages occurring at these loads. Another way to analyze the deformation response of the structure to the static load is acoustic emission testing. These pictures show the change in the number of acoustic emission signals in the loading process. Similar to the previous cases, we can note the loads of about 80 kN and 130 kN. These loads are associated with a rapid increase in acoustic emission signals. This phenomenon can be correlated with the occurrence of damages in the structure. We can notice a fast attenuation of A signals with a distance from the loading zone. However, even at the distance of 5 meters, these signals are reliably recorded. This slide summarizes data on the changes in the deformation response of the structure during loading, obtained by 3 different methods. The diagrams refer to the points number 1 and 2 adjacent to the loading zone. In all diagrams we can clearly identify the loads that correspond to a sharp change in the deformation response of the structure. They are about 80 kN and 130 kN. The detected features are most clearly manifested in the area adjacent to the jack location. So we can conclude that noticeable structural damages appear near the jack location and correspond to the above values of load. A physical experiment was carried out on a large-scale concrete structure, which made it possible to detect the changes in the mechanical state of the structure caused by increasing static load. Namely, the changes were recorded in the spatial distribution of the deformation parameters, the vibrational properties of the structure, and the spatial distribution of acoustic emission signals. Based on the analysis of experimental data, it was found that certain values of the load correspond to a sharp change in the deformation characteristics, vibration properties, and of acoustic emission signals. We believe that this phenomenon is associated with the appearance of inelastic deformation areas and local damages. The signs of the appearance of inelastic deformations, obtained using different methods, are in good agreement. The obtained results can be used in the development and implementation of automatic deformation monitoring systems. The developed approaches, methods and tools for assessing the critical state of structures can be used for a wide variety of engineering structures during their operation. Thank you for your attention.